Hello community! Welcome to AI and the Tomorrow Machine. Let's just jump right into the differences between a Monte Carlo Particle Filter and a Monte Carlo Tree Search. And if you say, hey, wait a second, what the hell are you talking about? Well, in my first video, we talked about the core of AI agents. In the second video, we talked about Monte Carlo empowered AI agents. And now in this third video, if you start new, never mind, we have a simple task. Let us find our best future for a particular environment, for a particular configuration that we set in our mathematical physical simulation. And we just want one question to answer. Can artificial intelligence help us? Can AI provide real value in my life? And not just generate profits for Microsoft. Now, in the last video, as I told you, particle filters primarily used for state estimation and dynamic system, where the goal was, as I showed you, to estimate the posterior distribution of the system state over time. Given we have noisy observation, we apply this in robotics and, of course, in system dynamics, where we have non-linear and non-Gaussian distribution of our data. And now we use again Monte Carlo, but now we use it in a different application. We go for tree search. And yes, I know you have this in your MATLAB libraries, you have this in your Python, in your C++, wherever you go on GitHub, you find this. But now we're going to implement this in a particular way. Let's have a look. The difference is now here for the state optimization for the sequential Monte Carlo. Now for the tree search, we go for the decision making. MCTS is used for decision-making problems like game playing and other scenarios where one AI agent must select or should select the best action from a set of possible action by, and now this is the interesting part, by simulating future states and outcomes. So the AI defines its internal future given its knowledge, given the capacity and the pre-trained and fine-tuned parameterized knowledge of your LLM, of your vision language model. And then we apply this. And Go, or maybe AlphaGo, we apply it normally in reinforcement learning, but now we are applying here in the planning problems where the goal is to make a decision that maximizes here the future rewards if we have a game set environment with multiple players. Now, for my green grasshoppers, it is very simple. Just remember, particle filters are for state estimation in dynamic system, and the Monte Carlo Tree Search is for decision making. Finding here the optimal actions by simulating, by computer simulation, and evaluating potential futures. And those potential futures are defined. We have to define them in the boundary condition. And then we have to define an evaluation procedure, and we have to define the interdependencies of the hidden factors and everything you know from Monte Carlo Tree Search. And this was the reason why those simulating and evaluating our potential futures in our environment, I call this the Tomorrow Machine. Now, you might say, hey, this sounds simple, but are you truly sure? Because can you see here the tree structure in this graph? And can you do then a computation? Well, let's start at the beginning, and we have here this beautiful paper here from California Institute of Technology, NEC Laboratories America, University of California, LA, Shenzhen University, and Rensselaer Polytechnic Institute. And they go here exactly for learning strategic skill by LLMs or vision language models, doing now here Monte Carlo Tree Search in multiple ways. So let's have a look at this. This is the official explanation as presented in the paper by the authors. And you might say, hey, that looks easy. No, that sounds easy. Absolutely. So for my green grasshoppers, let me just reformulate the task that we have for our AI agents. Your task is generate new strategic skills for yourself or another agent in your gameplay. The task is winning a multi-agent game. And now your tools are, you have self-play simulations that you can use as a tool, and you can implement a Monte Carlo Tree Search algorithm in advanced when I show you the code in a minute. And we have some LLM to provide us a feedback and a selection process. You say, okay, bene. Now, If you want to go there in detail, I have written here the 4 major steps that I see interpreting here this paper. But of course, there's an easy way to see this. Look, it just starts by you have a strategy for a particular problem, for a particular environment. Maybe you have multiple strategies in your pool of strategies. So you choose one particular strategy. The game starts. And now you have an LLM that, taking this strategy, says, hey, I have a new idea for this particular strategy to further increase the performance of this strategy. And let's call this strategy now Strategy Plus. Now, the idea is simple. You have to apply this Strategy Plus now in a computer simulation. You simulate here how good is it better than the old strategy. So you test Strategy Plus in a computer simulation. You do this with Self-play with the Monte Carlo Tree Search. If you're not familiar, Monte Carlo Tree Search is used to explore future outcomes. Simple. It performs and evaluates the different future scenarios. That's all that it is doing. Here now a little bit more detailed information about the tree search. Involves 4 main steps, iterated repeatedly to build a search tree dynamically based on the results of the simulated playouts. So here, each step, first selection. You start at the root node in your graph, and an algorithm selects successive child nodes down to a leaf node, a node at the current frontier of the tree, and the selection is guided by a policy that balances here the exploration and the exploitation. And you know we have here the upper confident bound formula applied to trees where, those are the number of the moves, and I hope you know this formula. Second step is now the expansion. If the leaf node can be expanded, if it has unexplored child nodes, which we hope, 1 or more child nodes are added to the tree. So this step increases now the breadth of the tree and is essential for exploring new potential outcomes. Step number 3, simulation. From the new nodes, the algorithm simulates an outcome using here a random playout policy, simply simulates here the game or decision-making process from the node to a terminal state using random choices. And I've shown you in my last video multiple agents for random choices. And the result of this simulation provides an estimation of the node's value. So, you remember I showed you here Monte Carlo, the simplest way, find the hidden parameter pi. This is easy. And now we just have the question here, if we have here a multidimensional topic, if we have those nodes, we simply ask, hey, what can this particular node achieve for my future? What can it do in my future scenario that I evaluate against my task? And then, don't forget step 4, backpropagation. After the simulation is run, the results are propagated back up the tree. So this simply involves updating the nodes along the path from the selected node up to the root with the outcome of the simulation. Was it a win? Was it a loss? Was it a tie? Whatever. You have some outcome that you want to update here. This update modifies the statistical information at each node, which will influence future selection steps. This is the explanation by GPT-4 Turbo, but I know you all want to see here the explanation by GPT-4 Omni after I uploaded here a little bit of material about here the tree search algorithm to GPT-4 Omni. Now, if we have this, you can, and I will show you the code. The code is completely available. It is open source. You can take it. You can play your particular game with this. But I decided to put in a little additional element and coming back here with a set of actions that the LLM choose, and I found out here by Monte Carlo Tree Search, I added a filter. Now, a filter can be whatever you like. And one condition on my filter was, for example, I don't want to cheat. Or I don't want to lie to the other players here. So whatever you have, maybe you have an ethical filter, or you want to restrict yourself to a certain set of rules here. So whatever you like, you can implement a filter, update the strategy, and then the cycle starts all over again. There is a beautiful documentation. Thank you to all the authors here. And I would recommend this, LLM Strategist, GitHub.io. There you have it, you have the paper, you have an archive, you have the GitHub code, you have a particular video, and you have a Google COLAB. I mean, what else can you wish for? look, this is the COLAB here, Strategist here for a particular game, you have a playground, and you can play with this configuration. Or you go here to GitHub and you can play here another game, Avalon, and you have the benchmark and the agent and everything beautiful. But what I was interested in was the code here for this tree search that is now implemented in the Strategist. And as I already showed you, you go here just to the directory, and under Strategist Searchlight algorithm, you have here the best first search, the full search, or here the Monte Carlo Tree Search algorithm implemented. You just go there. It's running, it's available for you, it's coded for you. You just input the parameters that you like, the game that you like, the conditions that you would like to change, or just take it, copy it to, I don't know, some code LLM, let you explain each step of the code. So this is a great example that you can go step by step. Talking about example, there are a lot of examples given in the publication, but I personally would like to give you my example. And I would like to stress here for a legal reason that, of course, this is only a theoretical example. And thinking about, does AI have a value for me, a real value, I mean? And I'm just not talking about summarize an email or send out an email with best wishes for a birthday. I want to create value in my life. And reading this paper, I thought, hey, I can apply this to something, to a topic that concerns me personally. So I've chosen, or I created now this example that I would like to show you. And I say, hey, we use now AI to optimize here a treatment plan for a chronic disease management. And let us say that we have here a person, and maybe in a theoretical case, this person is me, and I have a medical condition. Maybe diabetes. And now I'm not, let's think that I'm not in a price bracket where I can say, yeah, just go for several weeks to a specialized clinic and they will do all the adjustment here of my drugs and perfect personal treatment and everything. Imagine I cannot afford this. And then I have a simple idea. Theoretically, of course, can I use my knowledge on AI to kind of optimize here? I don't feel taken care of. Yes, I got some medicine, but otherwise, I ask, can I optimize this with my knowledge? So, scenario, we have now somebody trying to develop a treatment plan for patients with diabetes. So the goal is to optimize here the treatment plan to improve the patient outcome. So, one condition is maintain stable blood glucose levels. The current strategy is everybody gets the same standard treatment, independent if you're a man or a woman or if you're a child or whatever. This includes your fixed medication dosage, a diet, an exercise routine prescribed here to all the patients alike, and. And now I thought, so if I would have an LLM that can review here my personal data, and I have here, all the different recording devices here from, I don't know, if you do some exercise, maybe you have your Apple Watch or you have your Android Watch or whatever little gadget you have, you create personal data every day in your life. And now maybe we can use those data. So past patient outcomes include some blood glucose levels adhering to the treatment plan and side effects. And the LLM now suggests a new idea. And we go now to this exact paper, but we apply it now to a topic that might create some individual value in a theoretical example. And the LLM would say now, hey, maybe we should personalize the treatment plan based on the individual patient responses to the medication and the lifestyle factors. So LLM might say, hey, some patients might benefit from a lower dosage combined with some increased physical activities, while others may require more medical adjustments from some other whatever. So you see, we have now standard scenario, the LLM has a new idea, tries to implement this idea, and now this is great. Now, in another theoretical example, you can say, okay, imagine you are at a hospital and you have a team of medical doctors and they come together And together they have data about thousands and thousands of patients that suffer from a theoretical chronic condition. Imagine they would have the personal data respecting here the privacy of each and every individual, of course, but at the hospital level, they would have here data where they would have an age group of very young to very old, and a group of people that weigh just 50 kilograms to people that weigh 300 kilograms. If they would have all those data, timelines over years and years, and maybe some of the patients have taken daily notes, how they feel, what they've done, what is their condition, what they would like to explore next for them, if all those data were available. And then all those medical doctors would sit together with maybe some expert in AI, and they ask, hey, can we generate an LLM which would be able to learn on a different cohort of our theoretical patients so that we can build upon what we have on empirical data? And then can we maybe add new ideas? So step 2 now in our theoretical example of optimize the treatment plan for chronic disease management of maybe me, there is now storing and prioritizing idea in the idea queue. So the system, this is maybe the LLM, adds a new idea to an idea queue with a score, let's say 3.7, reflecting its potential to improve the patient outcome based on initial analysis. Now, in our theoretical example of a group of medical doctors and who have thousands and thousands of patient data, they would be able to say, hey, look, this actual patient of mine now, he is similar to a very tiny subgroup of those thousands and thousands of patients, and maybe we can take now in our idea queue something that worked in the past for those other people that had the same conditions. So we have now in the queue a new element, let's call it idea B, personalize the treatment based on individual response and lifestyle factor. And let's say this worked in the past for similar people, for similar humans, similar patterns were discovered. So we give it a score of 7.2. Now step 3 is refining the strategies. But now the important part, we do a self-play computer simulation with Monte Carlo Tree Search. Might sound simple, but maybe it is not that simple. So let's strategy selection. System selects a standard treatment plan and decides to implement a personalized approach suggested by idea B to see if it leads to a better patient outcome. So creates now a modified treatment strategy that tailors medical dosage, diet, and exercise recommendation based on each individual patient's unique medical history and current conditions. And if we, in our theoretical example, let's say we are a pharma conglomerate, and we have patient data, or we are in a hospital and we have thousands and thousands of patient data, we could do this theoretically and have then the data respecting all the legal requirements and respecting all the patient privacy, and then that we have now an idea about medical history and current conditions, and the system now may suggest a slightly reduced medication for a patient with a history of whatever combination of hidden parameters there are. And now we have, or the system itself has to have some computer simulation that it can run itself multiple times. So the system could simulate this new idea, how it works out, by applying now this personal treatment plan to a virtual patient or a virtual patient profile given the historical data that we have, which represent different combination of health parameters. As I told you, a specific age, a specific weight, previous responses to treatment, other medical conditions. If we have the data, an AI could find similar patterns in it. And now comes the beauty why we need Monte Carlo here Tree Search, because now it simulates different scenarios where the patient now follows the personalized plan versus the standard plan, considering now factors like adherence, potential side effects, overall health outcomes. And this software simulation, but careful, you really have to have the right software package with the right parameters that apply to your individual case in this only theoretical scenario. So this software simulation must really map reality one-to-one on this simulation level, and then it might show that the personalized plan might lead to a better control of a particular parameter and maybe have fewer side effects. So you see what our Monte Carlo Tree Search does here. Then step 4, of course, we have to evaluate here. Performance evaluation, the system analyzes the simulated outcomes. Suppose the personalized treatment strategy improves now the outcome in our computer simulation for 80% of the virtual patients compared when we have a standard plan, the same thing for everybody. And then the feedback updates the strategy library, and in this library it has hundreds of potential strategies that might be useful or in the history has been applied and were really helpful for individual patients with their individual parameters. And with this refined treatment plan, they can increase now the score of this new idea, do something personalized to this patient. And in the idea queue, we have now also another idea, since we have demonstrated the effectiveness. Now update the queue. The idea queue score increases, reflecting now the success in improving the patient outcomes. So this idea becomes now a priority for further refinement. So in the second run or in the third run, the system in its memory knows, hey, I don't go here for the standard plan, but I go here with a personalized plan. And it builds upon this, and then it runs another, 10, dozens, 50, 100 new idea generation. And in the computer simulation, they try to find out here now the perfect configuration for a particular theoretical patient. Step 5, iterative process. As I just told you, it goes on in a cycle. System tries to optimize itself, might now explore further refinements. The LLM generates new ideas. Maybe they are crazy ideas, but maybe they are real sound ideas. Maybe the LLM goes out and do some internet research about the latest paper and comes back with those ideas, and then tries to implement this into software simulation packages in the libraries that it can run, C++, Python, whatever there is, and tells us, hey, if we do this, then we have a better performance of the patient. So adjusting the treatment plan in real time based on continuous monitoring of the patient health data, such as wearable devices to track here the glucose level, then we can now really validate, verify that for this individual theoretical patient, this theoretical personalization really works and improves here the well-being of a human. So you see, time and time goes on, and if we integrate here an artificial intelligence in the loop with this methodology, by this publication that I've shown you here, with the Monte Carlo Tree Search, over time the treatment plan might become better, more adaptive and more personalized, leading to a better long-term management of the chronic condition, and hopefully we achieve an overall patient well-being. So let's see, in our theoretical example, this group of medical doctors or this pharma institution that acts globally, if they have the data, I think with AI, there is now a real possibility applying our understanding of AI in a particular way, looking at the latest research from all the universities on this planet. I think there's a real potential that AI can generate value on an individual level for, let's say, my theoretical condition, for my personal well-being, for my body. And this makes me hopeful in a certain way. Because, maybe it's really true, the future is yours to create. But you know what? I discover now here at the end of this video today that there is in the research literature in AI now an emerging topic. And this topic is not about inference, but this topic is more and more about pure forecasting. How can we use AI to do the forecasting for particular systems, for particular medical conditions, for particular financial constellations? How can we use agents? How can we improve the skill level of agents? How many agents do we have to add to a system? How complex can the agent interaction be? Do I have still to have here a super agent and then all the other minion agents? How can we optimize here the, let's call it, distributed AI computation and the distributed AI intelligence between agents? And if you all apply this to the forecasting, I think this will be one of the main topics of AI for the rest of this year. And maybe my next video, I added a surprise to all of you, will be about forecasting. Let's see. I hope this video, although it was theoretically a little bit personal, that you enjoyed it. Maybe you got a new idea. Maybe you completely disagree with me, which is perfect in any way. I would appreciate you leave a comment here in the description of this video. And it would be great to see you in my next video.